Tesla's promise of a truly affordable mass-market electric car has hovered over the auto industry for years. The company revolutionized the perception of EVs with the Model S, then pushed into broader adoption with the Model 3 and Model Y, but for many buyers, even Tesla's entry-level models remain out of reach. That's where the company's next-generation compact vehicle, often referred to by fans and analysts as the Model 2, comes in. Central to making that vehicle genuinely cheaper is a new wave of battery technology Tesla is targeting for the middle of this decade. In this report, we examine how Tesla's evolving battery strategy, expected to mature around 2026, could dramatically cut costs and make a lower-priced Tesla financially viable, without sacrificing range, performance, or profit. The core challenge is simple: batteries are still expensive. While EV prices have fallen over the last decade, the battery pack remains the single largest cost item in an electric vehicle. Depending on the model and chemistry, the battery can represent 30 to 40% of the total cost of the car. For Tesla to sell a compelling compact EV in the roughly $25,000 range and still make money, battery costs have to drop substantially, both on a per kilowatt-hour basis and in the amount of battery capacity the car needs in the first place. That is the problem Tesla's mid-decade battery tech is designed to solve. Tesla has hinted at this strategy in several high-profile presentations. At its 2020 Battery Day, the company laid out a roadmap to cut battery costs by roughly half over the long term, using a combination of new cell formats, new materials, new manufacturing methods, and tighter integration between the battery and the car's structure. Then at its 2023 Investor Day, Tesla described a next-generation vehicle platform it said could reduce overall manufacturing costs per vehicle by around 50% compared with the Model 3 and Model Y. The battery is a huge part of that math. While Tesla has not officially named this future compact car and has not committed publicly to an exact launch year, industry watchers widely expect a smaller, cheaper Tesla around the middle of the decade, with 2026 a frequently cited target window. The battery technology underpinning that car is taking shape now. Before we look at what's changing, it helps to understand where battery costs stand today. A decade ago, battery packs routinely cost several $100s per kilowatt-hour. That made electric cars prohibitively expensive except at the very high end. Thanks to advances in chemistry, manufacturing, and scale, industry-wide battery pack prices have fallen dramatically. By the early 2020s, many analysts estimated average pack costs below $150 per kilowatt-hour, with leaders like Tesla and top Chinese manufacturers likely achieving even lower figures in certain models. But for a truly affordable compact Tesla, the bar is lower still. Many experts point to a range in the neighborhood of $60 to $80 per kilowatt-hour at the pack level as the zone where a $25,000 EV becomes much easier to achieve at healthy margins. Tesla's mid-decade roadmap is essentially a campaign to get into that zone through multiple simultaneous improvements. A key pillar of Tesla's strategy is the move to a new cell format, the 4680 cylindrical cell. Those numbers refer to the dimensions of the cell, 46 millimeters in diameter and 80 millimeters in height, making it significantly larger than the 2170 cells used in many current Teslas. The 4680 cells were first detailed at Battery Day and are already being produced in limited volumes. But the real payoff is expected as the technology matures and manufacturing scales up through the middle of the decade. The design is tabless, meaning the current collectors are integrated along the length of the cell, reducing resistance and simplifying assembly. Larger cells mean you need fewer of them to build a pack of a given capacity, which in turn means fewer welds, fewer parts, and fewer manufacturing steps. In principle, all of that translates into lower cost. However, simply making cells larger is not enough. They must be cheaper to produce and reliable at scale. Tesla's goal with the 4680 is to increase energy stored per cell, improve the amount of energy stored per unit of material, and reduce the capital expense per gigawatt-hour of factory output. When the cells first appeared in production, they did not yet meet all of Tesla's ambitious targets, and output volumes were modest. But the company signaled that its learning curve would be steep. As manufacturing lines are debugged, yields rise, cycle times shrink, and material utilization improves, cost per kilowatt-hour falls. By the time the next generation compact vehicle arrives in significant volume, Tesla expects those 4680 lines, or their successors, to be substantially more efficient and cheaper, delivering the kind of per-cell cost reduction that a low-priced Tesla demands. Parallel to this change in format is an equally important shift in how the battery pack is integrated into the car. Tesla's structural battery pack concept, already in limited use, turns the battery from a separate component into part of the load-bearing structure of the vehicle. Instead of building a full underbody frame, then bolting a battery pack into it, Tesla's structural pack design uses the battery itself as a stressed member, sandwiched between large front and rear castings. That approach eliminates a significant number of parts, welds, and fasteners. It can reduce weight, improve body stiffness, and critically simplify manufacturing. By 2026, Tesla's vision is to pair a mature 4680 style cell with a fully optimized structural pack and large, gigacast front and rear sections, turning the car, underbody into what is essentially three big pieces: a front casting, a structural battery pack, and a rear casting. That underbody redesign has massive implications for cost. Fewer parts means fewer stamping presses, fewer robots, and fewer workers needed to assemble a given number of cars. The factory floor becomes more compact, capital equipment requirements shrink, and production can be ramped more rapidly. For a smaller, cheaper car where margins are tighter, cutting assembly cost is just as important as cutting cell cost. Tesla has said its next-generation vehicle platform will drastically reduce the complexity and length of the assembly line. The battery, as a structural element, is at the center of that change. The savings that show up as manufacturing efficiencies in a financial presentation are, in practice, heavily driven by these battery-driven architecture choices. Alongside physical architecture, chemistry is the other half of Tesla's battery cost story. Today, Tesla uses a mix of battery chemistries depending on the model and the region. Long-range and performance variants often use high-nickel NCA or NCM chemistry, which offers high energy density but relies on more expensive metals like nickel and, to a lesser extent, cobalt. Standard range models in several markets already use lithium iron phosphate, or LFP, chemistry. LFP is less energy dense, so it requires a slightly larger and heavier pack for the same range, but it has key advantages. Iron and phosphate are far more abundant and cheaper than nickel and cobalt, and LFP cells tend to have long cycle life and good safety performance. For a compact car aimed at affordability rather than maximum range, those trade-offs are acceptable and indeed attractive. This is where Tesla's 2026-oriented battery strategy becomes more pointed. Analysts expect that the company's future low-cost compact will rely heavily, if not exclusively, on LFP or similarly low-cost chemistries for most variants. That immediately takes a bite out of the bill of materials. No high-priced nickel, no cobalt, and a smoother path to sourcing raw materials at scale. But Tesla's approach is not simply a matter of picking LFP and calling it a day. It is about optimizing the entire vehicle around the strengths and weaknesses of that chemistry. LFP's lower energy density, for instance, can be offset with an efficient, lightweight car and an honest range target suited to urban and suburban driving, perhaps in the 250 to 300 kilometer range for base models. That allows a smaller battery pack, saving both material and cost, while still meeting most customers' daily needs. Tesla has also signaled interest in manganese-rich chemistries as a potential middle ground between LFP and high-nickel cells. Manganese is cheaper and more abundant than nickel, and certain manganese-heavy cathode formulas promise better energy density than LFP at lower cost than traditional nickel-based chemistries. While Tesla has not yet rolled out a manganese-dominant pack at scale, the company has repeatedly mentioned manganese in public presentations as an area of development. If that effort bears fruit around mid-decade, it could power variants of the compact car that need more range or performance without jumping all the way back to high nickel costs. In other words, chemistry options give Tesla a toolkit: LFP for the cheapest versions, potentially manganese-enhanced cells for mid-tier variants, and high nickel only where absolutely necessary. On the anode side of the cell, Tesla is pursuing another lever for cost and performance: silicon. Most lithium-ion batteries today use graphite as the primary anode material. Silicon can store far more lithium per unit of weight than graphite, which means that adding silicon to the anode can significantly boost energy density. At Battery Day, Tesla described a plan to use more silicon in a simpler, cheaper way than traditional approaches, avoiding some of the expensive processing steps that have held silicon back. The challenge is that silicon expands and contracts dramatically as it charges and discharges, which stresses the material and the cell. Tesla's long-term goal is to incorporate more silicon without making the cells fragile or too expensive to produce. If successful, that allows more energy per cell, or the same energy from less material, pushing cost per kilowatt hour down further and enabling smaller packs for a given range. Perhaps the most radical part of Tesla's battery plan is not what is inside the cell, but how the cell is manufactured. The company's acquisition of Maxwell Technologies and its work on dry electrode manufacturing are aimed squarely at the expensive and energy-hungry process of coating electrodes. In conventional cell production, cathode and anode materials are mixed into a slurry with solvents, coated onto a foil, then passed through large drying ovens and solvent recovery systems. This is slow, capital-intensive, and consumes a lot of energy. A dry electrode process eliminates the solvents and the bulk of the drying phase, depositing active materials in a dry form directly onto the foil. Tesla has said this can dramatically shrink the factory footprint required per unit of capacity and slash the cost and time needed to bring new cell lines online. By 2026, if the company successfully scales dry electrode technology, a gigawatt-hour of new capacity could be much cheaper to build and operate than in older plants. That factory-level innovation matters enormously when we zoom out to the global scale Tesla is targeting. The company talks about producing millions and eventually tens of millions of vehicles per year. For a low-cost compact Tesla, that level of volume isn't just helpful, it's essential. Low-margin products rely on scale to be profitable. Tesla's vision is for battery manufacturing lines that look less like traditional auto plants and more like high-throughput, densely packed, highly automated production machines. If dry electrode coating, optimized 4680 style cells and structural packs can all be designed into a single continuous flow, the cost per battery pack, and therefore per car, can fall sharply. Smaller plants can produce more capacity, capital expenses can be spread over more units, and the energy cost of producing each kilowatt hour can be cut. To support that scaling, Tesla has been moving upstream into the raw materials and intermediate stages of the battery supply chain. The company is building its own cathode materials facility near its Texas factory and has announced plans for a lithium refinery in the state as well. It has struck long-term agreements with lithium producers and other mineral suppliers around the world. By owning more of the process, from refining raw lithium to producing cathode powders and finally assembling cells, Tesla aims to reduce its exposure to price swings, cut out middlemen, and better control quality and cost. For a low-priced compact packed with relatively low-margin LFP cells, shaving even a few dollars per kilowatt-hour off material and processing costs can be the difference between a merely cheap car and a game-changing one. Battery efficiency is not only about cost per kilowatt-hour, it is also about how many kilowatt-hours you actually need in the vehicle. Here, Tesla's broader engineering and software strengths come into play. More efficient motors, inverters, and drivetrains mean the car can travel further on each unit of energy stored. Lightweight materials and aerodynamic design further stretch range without adding battery capacity. And Tesla's continuous software optimization, from thermal management to energy-aware routing and navigation, can squeeze more real-world utility out of a smaller pack. The result is that a compact Tesla might achieve acceptable range with, for example, a 40 to 50 kilowatt-hour pack instead of something larger. If mid-decade battery costs can be pushed toward, say, $70 per kilowatt-hour at the pack level, that means a total battery cost in the ballpark of $2,800 to $3,500 for the base vehicle, potentially half or less of what an equivalent pack would have cost just a few years earlier. Of course, the battery is only part of the bill of materials, and Tesla's next-generation platform aims to cut cost across the entire vehicle. The use of large front and rear gigacastings, simplified wiring harnesses, and more modular subassemblies should all reduce labor and parts count. But the battery remains central, because many of these changes are enabled by how the pack and structure are integrated. Without a structural pack, the underbody would require more traditional stamped steel components. Without compact, high-output cells, pack thickness and weight might force compromises elsewhere in the design. By co-optimizing the battery in the car, Tesla is trying to capture compounding improvements, each of which contributes a slice of the overall cost reduction pie required for a truly affordable Tesla. To understand why this push is urgent, it is important to look at the competitive landscape. Chinese automakers, led by companies like BYD, are already selling lower-cost electric cars domestically, many using LFP batteries and highly optimized platforms. BYD's Blade-style LFP battery and integrated e-platform architecture are examples of how tight cell-to-pack integration and low-cost chemistry can create compelling, affordable EVs. As these companies begin to export more aggressively, they put pressure on legacy automakers and on Tesla alike. For Tesla, matching or beating those cost structures, while maintaining its brand, software ecosystem, and charging network advantage, is critical. The 2026 battery tech roadmap is, in many ways, Tesla's answer to that challenge. There are, however, significant risks and uncertainties in the plan. Scaling 4,680 style cells to the volumes required for a global compact car is not trivial. Early production has faced yield and ramp-up challenges, as is common with new cell formats. Dry electrode coating, while promising, is technologically demanding. Achieving uniform, high-quality coatings at high speed has proven difficult for the entire industry. Supply chains for lithium, phosphate, and other materials must expand in a sustainable way, and new refineries and processing plants must be permitted, built, and brought online. Even the structural pack concept introduces engineering complexities, from crash behavior to repairability, that must be fully validated. Tesla has to solve all of these challenges concurrently while keeping timelines and budgets under control. Market dynamics add another layer of complexity. Consumer expectations for range, charging speed, and in-car features continue to rise. A lower-priced Tesla cannot simply be a stripped-down version of today's models. It must feel like a modern Tesla, with strong performance, good range, access to the supercharger network, and an appealing interior and software experience. Each of those expectations can pull against cost-cutting efforts. Regulators, too, are tightening safety and environmental standards globally, which can add engineering requirements and compliance costs. Tesla must navigate all of that while staying ahead in software features like driver assistance, which themselves require expensive hardware and computing platforms. From an investor's standpoint, the stakes are high. A successful low-cost compact built on mature, low-cost 2026-era battery tech could dramatically expand Tesla's addressable market. Instead of targeting primarily middle and upper-income buyers, Tesla could tap into the much larger pool of mainstream car buyers who currently choose compact gasoline or hybrid models. That would not only increase unit volumes, but also deepen the company's ecosystem of software subscriptions, connectivity services, and potential future revenue from autonomous driving features. Conversely, if battery costs do not fall as planned, or if Tesla struggles to industrialize its new technologies, the economics of such a car could be far less attractive, forcing higher prices or thinner margins. The timeline is another source of debate. While 2026 is often cited by analysts and commentators as a realistic timeframe for Tesla's next-generation compact, and for its associated battery tech to be fully ready, the company itself tends to avoid hard dates until projects are very near completion. Tesla's history includes ambitious schedules that have slipped as the realities of manufacturing complex systems set in. That said, nearly all of the pieces of the 2026 battery puzzle are already visible in some form. 4680 cells in limited production, LFP packs in current standard range models, structural pack designs in certain Model Y variants, new factories under construction or expansion in multiple regions, and a clear corporate focus on lowering cost per vehicle. The direction of travel is clear, even if the exact arrival date is not. What does all of this mean for the consumer who simply wants an affordable electric car? If Tesla's battery roadmap unfolds roughly as outlined, a compact Tesla around the middle of the decade could offer a compelling combination: enough range for daily use, access to fast charging, the performance and software experience associated with the brand, and a price point that undercuts many current EVs and potentially rivals gasoline compacts on total cost of ownership. Lower battery costs would allow Tesla to absorb price competition, offer more generous financing or lease terms, and still protect its profit margins. It could alter the price expectations for EVs across the board, forcing competitors to accelerate their own battery cost reduction efforts. Stepping back, the story of Tesla's 2026 battery tech is about more than any single innovation. It is about stacking many incremental advantages on top of each other: a larger, more efficient cell format, cheaper, more abundant chemistries like LFP and potentially manganese-rich cathodes, smarter anode materials, radically more efficient manufacturing through dry electrode processes and highly automated gigafactories, vertical integration into cathode production and lithium refining, structural integration of the pack into the car, and ongoing gains in vehicle efficiency that shrink the required pack size. No one of these changes delivers the full cost reduction needed for a truly cheap Tesla, but together they can. In the end, the answer to how Tesla's mid-decade battery technology cuts cost to make the so-called Model 2 cheaper lies in that accumulation of detail. By designing the cell, the pack, the factory, and the vehicle as a single system, and by pushing each element down the cost curve simultaneously, Tesla is trying to reach a point where an electric compact car is not just environmentally attractive or technologically impressive, but simply the obvious economic choice for millions of buyers. Whether that vision lands precisely in 2026 or a bit earlier or later, the direction is clear. Batteries are moving from being the limiting factor in EV affordability to being the engine that finally unlocks it.